Hello everybody, welcome back to ATM 5, Our Changing Atmosphere. In today's lecture, we're going to dive into the science of energy, the processes by which energy moves around the Earth system, and what determines the distribution of energy reaching the Earth's surface. In today's lecture, we'll be defining temperature, conduction, convection, radiation, energy balance, blackbody, solar constant, and insolation. Our key questions to answer today are: why is energy balance a good approximation for the Earth system? How does insolation change by latitude? How does insolation change by season? How is insolation connected with the local climatology? And why is the top of the atmosphere insolation different from surface insolation? Okay, to understand energy and the Earth system, first we need to understand what exactly energy is. We're particularly interested in kinetic energy, which is energy because of motion. This kind of energy can exist at the macroscopic level, for instance, a ball that's flying through the air, or at the microscopic level, where individual atoms are flying around. When you have a lot of molecules all flying around, bouncing into each other, it might seem from very far away that the molecules aren't moving at all as a group. But these vibrations are still storing a lot of energy. The average kinetic energy of this group of molecules is thus called its temperature. So cold air is simply a big collection of air molecules that aren't moving around very quickly. They are moving relatively slowly and carrying less kinetic energy. Hot air, on the other hand, is just air molecules that are zipping around rapidly, carrying more energy. Kinetic energy, and thus temperature, gets transferred in several ways. Temperature can be transferred via conduction, which is simply heat transfer due to contact between a warm object and a cold object. Molecules in the warm object bang against molecules in the cold object, causing those cold molecules to move faster and warm molecules to move slower. If this happens, then the warm object or gas will seem to cool down, and the cold object or gas will seem to warm up. Temperature can also be transferred via convection, which is heat transfer due to movement. If a blob of warm air moves into a room full of cold air and then dissipates, the average temperature of the room will increase. Finally, temperature can be transferred via radiation. This is pretty similar to transfer via conduction, except the transfer is managed by small particles known as photons, little bundles of radiated energy. Objects are constantly emitting and absorbing photons. When these photons are emitted, the object loses a bit of energy when the photon flies away. When a photon is absorbed, the object gains a little bit of energy from the photon. This last form of energy transfer is the dominant driver by which energy is exchanged within the Earth system, and hence it'll be our focus for the next 2 lectures. Of these 3 mechanisms, radiation is the most important for understanding the science of climate change. So let's talk about photons for a minute. Photons are pretty basic creatures. They always travel at the speed of light and can't be broken up into anything simpler. You can also learn everything about a particular photon with just one number, namely its wavelength. As photons travel through space, they oscillate up and down. The distance it takes for a photon to go through one cycle of that oscillation is known as its wavelength. If the wavelength is small, then the photon is oscillating really rapidly and has a lot of energy. If the wavelength is large, then the photon is oscillating slowly and has very little energy. For a particular range of wavelengths, namely between 380 nanometers and 740 nanometers, photons are visible to our eyes and so are referred to as visible radiation. At shorter wavelengths or higher energies, we have other forms of light you might have heard of, including ultraviolet light, X-rays, and gamma rays. At longer wavelengths or lower energies, we also have infrared radiation, microwaves, and radio waves. All of these possible forms of light fall on what is known as the electromagnetic spectrum, which is depicted here. It turns out that temperature and radiation are intimately connected with one another. Perhaps not surprisingly, warmer objects emit more energy. Cooler objects emit less energy. Think about an electric stove. When it's cold, it's dark and radiating little energy. When it's hot, it's red and radiating away heat energy that's visible to our eyes. Physicists have a name for objects that behave perfectly when it comes to radiation. Namely, these are called blackbodies. idealized physical objects that absorb all incident radiation and emit radiation in accordance with a physical principle known as the Planck Law. This law of nature basically says what the chances are that your object will emit a photon with a particular wavelength. The key observation relevant to our study being that hotter objects will tend to emit more photons that are higher energy compared to cooler objects. The chart at the right here shows emission curves, that is, how much energy is emitted for objects at temperatures of 3,000, 4,000, and 5,000 Kelvin. The object at 5,000 Kelvin, a reasonable approximation to the temperature at the visible part of the sun, peaks in the visible part of the electromagnetic spectrum, meaning that it has the greatest probability of emitting a photon from this particular part of the spectrum. For cooler objects, their emission tends to come more from the lower energy part of the spectrum, here on the right. Here we see Planck's law itself is a rather nasty-looking equation. You won't be expected to memorize this unless it's appropriate for your field. All you need to know is that this complicated-looking equation was an amazing discovery for its time and explained how much energy we should expect at what wavelength for an object of a given temperature. If we take Planck's law and sum it over all wavelengths, that gives us the total amount of energy emitted by an object. It turns out that this expression is very simple. The total energy emitted is simply a constant, denoted here with a sigma, known as the Stefan-Boltzmann constant, times temperature to the fourth power, where the units of temperature here are in Kelvin. The resulting value is in watts per meter squared. That is, for every meter squared of an object, it emits that much energy per second. Watts here being a unit of measuring energy per second. This means that as the temperature of an object increases, the total amount of energy it emits increases rapidly. Okay, that's enough radiation for now. Let's go back to our discussion of energy. It is a fundamental law of physics that energy must be conserved. Namely, energy cannot be created and it cannot be destroyed. If one object warms up, then another must cool down. Every object has an energy bank account where it stores all of its energy. When energy is received, the object's energy bank account goes up. When energy is spent out or emitted, then the object's energy bank account goes down. If an object is in a state of energy balance, then much like a bank account in balance, the energy received must equal the energy emitted so that the total change is equal to zero. However, we also know that energy emitted is also proportional to temperature to the fourth power. The little fish-like symbol here means proportional to, and means that if the temperature doubles, then energy emitted must go up 16 times, equal to 2 to the power 4. Thus, if an object is in a state of energy balance, then we can actually calculate the temperature of that object using only the energy received. And we'll do that in our next class. However, if an object is not in a state of energy balance, it will tend towards that balance. If an object receives more energy than it emits, then the change in energy is positive, and the object will gain energy and thus will warm up. This causes the object to emit more energy. If an object emits more energy than it receives, then the change in energy is negative, and the object will lose energy and cool down. This causes the object to emit less energy. In general, then, the emission will tend to match that of energy received. So what does this imply for Earth? Well, we know Earth has had a very long time to equilibrate its temperature. And we also know that the energy received by the Earth does not change significantly on timescales of millions of years. Thus, we can conclude that the Earth system is, to a close approximation, in a state of energy balance. This means energy received by the Earth is equal to energy emitted by the Earth. Notably, energy balance is not affected by human activities. As we learned earlier, the amount of sunlight received by the Earth is not really affected by our activity on the surface. And if the amount received is only dependent on solar radiation, then the amount emitted by the planet must perfectly balance this energy received. So how can humans affect the Earth system? Well, we can change where that energy goes once it is received at Earth. If there is more greenhouse gas in the atmosphere, then we can trap that energy close to the surface and block it from leaving the planet. In that case, the atmosphere and oceans below that greenhouse gas layer can warm without our planet's total emissions of energy changing. Okay, now that we understand radiation, let's see what this means for the Earth. As discussed, the Earth is roughly in a state of energy balance. It must radiate energy at the same rate it receives it from the sun. However, the sun is much hotter than the Earth, with most radiation coming from the sun's photosphere at temperatures between 4,000 Kelvin and 6,500 Kelvin. To understand what kind of radiation, what kind of photons these two objects are radiating, we can approximate both the Earth and sun as black bodies. This allows us to use the Planck Law and Stefan-Boltzmann Law to understand what type of radiation is coming out. For simplicity, let's focus on the Stefan-Boltzmann Law. Since most energy is radiated from the sun's photosphere at a radius of 700,000 kilometers from the sun's center, we can use this law to calculate the total amount of energy emitted from the sun. To do so, we use the formula for the surface area of a sphere, 4 pi r squared, to calculate that area, then multiply it by the energy per unit area from the Stefan-Boltzmann Law. This gives a total emission of 3.87 times 10 to the 26 watts. For reference, a typical household uses 2,000 watts on average, and at any given time, the whole world only uses 1.14 times 10 to the 12 watts. So the total solar output could power around 340 trillion Earths. However, radiation from the sun shoots off in all directions, with only a small fraction of it coming in our direction. Most of it just escapes out to space. So we're really only interested in how much energy per unit area is actually accessible to us here on Earth. To calculate this, we need to consider how much light per unit area there is passing through a sphere as far away from the sun as the Earth is. Again, relying on our spherical surface area formula and using the fact that the Earth is on average 150 million kilometers from the sun, we find the actual energy we receive at Earth is only 1,367 watts per square meter. This value, 1,367 watts per square meter, is a special value known as the solar constant. It's a measure of the maximum amount of energy we can extract from the sun at Earth. If we had a satellite in orbit around the planet that could always be pointed at the sun and covered it with solar panels, 1 square meter of that satellite at 100% efficiency could collect at most 1,367 watts of energy. By comparison, most of our light bulbs from 20 years ago burn energy at a rate of about 100 watts. Note that in this discussion, we'd assumed that the Earth's orbit was perfectly circular, namely, that the planet stays at the same distance from the sun regardless of the time of year. This isn't quite the case as discussed last time, as the Earth is slightly closer to the sun at perihelion and slightly farther away at aphelion. These differences account for approximately a 7% difference in total solar radiation received by the planet over the course of the year. As noted earlier, the solar constant represents the amount of energy received by a satellite constantly pointing at the sun. However, for somebody standing on the surface of the planet, they're obviously not going to have the sun overhead at all times. So how much energy could we reasonably expect on the surface? To calculate that, we first need to calculate the total power incident on the Earth from the sun, all the energy that creates the Earth's shadow. If we had a giant screen behind the planet, the shadow would occupy a circular region with radius equal to the planet's radius, here denoted by A. The area of this shadow is thus pi a squared. If we calculate that area and multiply it by the solar constant, we'd get a total incident power of 1.74 times 10 to the 17 watts. Again, noting that global power consumption is 1.14 times 10 to the 12 watts on average, the total solar power incident on the planet is about 152,000 times the global power consumption. If the whole planet were covered with 100% efficient solar panels, this is how much energy we could extract. Now let's average that over the surface of the planet. Using the formula for the surface area of a sphere with the Earth's radius, we get approximately 341 watts per square meter of solar energy. So on average, each square meter of the Earth receives around 341 watts of energy from the sun, or enough to power just over 3 100-watt light bulbs. Modern solar panels improve on this a bit by tracking the panel with the sun. In that case, as long as the sun is up, those solar panels that track the sun can capture up to the solar constant in energy. But fixed solar panels on a house capture about half that. As we've discussed already, the direction of incoming solar radiation is important in determining how much energy is received per unit area. As you have probably noticed, when the sun is overhead, you're receiving the maximum amount of light from the sun. When it's low in the sky, you're receiving considerably less. Since the higher your latitude, the lower the sun will appear in the sky. These higher latitudes will be receiving considerably less energy. To think about this another way, if you've got two tubes of solar energy coming in from the sun, the tube that impacts the Earth directly perpendicular to its surface will cover less surface area than the tube that impacts the Earth at a higher latitude. Thus, the region closer to the equator will receive more energy per unit area than the region at higher latitude. That is, the region near the equator, where the sun is overhead, will receive more energy per unit area than, for instance, a subpolar latitude closer to the Earth's north or south pole. The amount of solar radiation received per unit area and recorded during a given time is commonly referred to as the insolation. In this case, the equatorial region has a higher insolation because the same energy is spread out over a smaller area. The polar region has a lower insolation because the energy is spread out over a larger area. That is, the insolation is equal to total energy incoming divided by area. In the case of the equatorial band, you have about half the area as in the polar band. So the denominator in the equatorial band is smaller than in the polar band, and so it is receiving more energy in the form of insolation. Seen another way, if at the equator light is coming in directly perpendicular to the surface, this region will be experiencing the greatest amount of energy per unit area. This leads to higher temperatures and widespread vegetation. In the mid-latitudes, around 45 degrees latitude, the same amount of energy is spread out over 1.4 times as much area, resulting in less energy per unit area. And in the subpolar regions, around 60 degrees latitude, the same amount of energy is spread out over twice as much area, producing much cooler temperatures on average. Because of the tilt of the planet and its variations in orbit, insolation is constantly changing. This plot shows the amount of energy that would be received under a cloudless sky at each latitude of the Earth's surface, going up the y-axis. The North Pole is at the top of this plot, and the South Pole is at the bottom. Brighter colors indicate more energy received, up to 550 watts per square meter, and black indicates that area is in complete darkness. As you move from left to right along this plot, it changes the calendar day during the year. We have the spring equinox in the northern hemisphere occurring around March 21st on the left-hand side of this plot, and we move throughout the year as we go across the plot, passing through the summer solstice, the autumnal equinox, and the winter solstice before returning to the spring equinox. The farther you are from the equator, the more extreme these variations are over the course of a year. At the equator, energy received is approximately 400 watts per square meter, roughly even over the course of the year. In the mid-latitudes, like in California, energy received is around 460 watts per square meter in the summer and 150 watts per square meter in the winter. At the poles, the variation is even more extreme. Summertime is under constant sunlight, with over 500 watts per square meter received, whereas wintertime is under constant darkness. However, there is also a significant difference between top of the atmosphere energy received and energy received at the surface. The top plot here shows annual average energy received at the top of the atmosphere over the globe, and the bottom shows surface radiation received. Why might these two be different? Of course, in between space and the surface lies the Earth's atmosphere. Both atmospheric gases and clouds play a big role in affecting radiation as it passes through the atmosphere. The net result is that even over the Sahara Desert, insolation drops from around 400 watts per square meter to 280 watts per square meter. Averaged over the whole globe, 25% of the incoming radiation from the sun is actually absorbed by the atmosphere, and 25% is reflected back to space. Clouds obviously play a big role in this. From the top, clouds are largely white surfaces, which you might remember from an earlier science class, are white because they reflect most incoming energy. Radiation that hits cloud tops has a good chance of being reflected back to space. So if we look where on the Earth clouds are present, in the ITCZ and in the mid-latitudes, particularly over the ocean where clouds are present more than 50% of the time, these are regions where a lot of incoming radiation from space will be reflected back. Okay, that's enough for today's discussion on temperature and energy. This lecture is the first of two that builds up our fundamental understanding of radiation in the Earth system. As we'll learn next time, radiation and the chemical composition of the atmosphere are closely connected with one another, and together determine the temperature of the planet. An understanding of this interplay also tells us why the greenhouse gases are responsible for warming the surface.